When examining the internal workings of large language models, there is a common fixation on the attention mechanism as the architecture's defining feature. This chart shows the parameter distribution inside a 175 billion parameter model. While attention handles the communication, roughly 2/3 of the model's parameters actually reside in a different structure, the Multi-Layer Perceptron, or MLP. To understand how a model actually remembers facts, we have to look inside these dense MLP blocks to see exactly how they store and retrieve knowledge. If attention is responsible for routing contextual information between words, the MLP acts as the vault for the model's baked-in world knowledge. During the attention phase, vectors representing different words project lateral connections to each other so they can share context. But as data enters the MLP phase, the network severs those connections. Each vector stops communicating laterally, moving strictly in parallel through isolated pipelines. Every vector undergoes the exact same mathematical sequence simultaneously, without any reference to its neighboring tokens. We can use the phrase Michael Jordan as a test case for how a specific factual association is retrieved in this isolated state. Because this processing is strictly parallel, we can see how the entire layer functions by following the geometric journey of just one vector. Consider a single input vector, E. Thanks to a previous attention step, this vector has already ingested the combined context of the tokens Michael and Jordan. First, we multiply this input vector by a massive weight matrix called the up projection matrix. Each row acts as a directional probe. Taking the dot product between a row and vector E produces a single scalar value. This dot product serves as a measure of alignment. The more similar the directions of the two vectors, the higher the resulting number. If row 1 represents the Michael plus Jordan direction, a high scalar output indicates that vector E perfectly aligns with that specific feature. The up projection matrix is effectively asking thousands of simultaneous geometric questions to determine which semantic features are present inside the input vector. Pure linear alignment has a problem. This matrix multiplication would also trigger high values for overlapping but incorrect concepts, like Michael Phelps, because the first name aligns. To solve this, the model applies a bias parameter, adding a specific negative value to the scalar output we just calculated. This negative bias acts as a strict threshold. Only a strong dot product can overcome it and remain positive. The resulting value then passes through a ReLU function, which simply clips all negative values down to 0. Combining the dot product, the negative bias, and the ReLU function creates a high-dimensional AND gate. This ensures that an artificial neuron only fires, remaining positive, if the exact, precise combination of features is fully present. The data is now in a sparse format, a long list of mostly zeros, alongside a few activated positive numbers where the model recognized specific concepts. This sparse vector drops through a down projection matrix, returning it to its original dimensional size. The matrix columns act as stored concept vectors, like basketball. We scale the active neuron's corresponding column by that neuron's value. Because the Michael Jordan neuron fired, its corresponding column vector is scaled up and physically added back into the original token vector. This addition appends the basketball direction to the vector, updating the data stream with the retrieved fact. The down projection matrix is the actual repository of facts. It injects baked-in knowledge back into the vector based on which specific neurons fired in the previous step. If we zoom back out, we see this exact sequence of probing and injecting facts happening to thousands of tokens simultaneously. This involves hundreds of millions of parameters per matrix, repeated across nearly 100 distinct layers in a model like GPT-3. But even at this scale, there is a paradox. The real world contains far more facts than the network has neurons to hold them on a one-to-one basis. This is solved by a concept called superposition. In high-dimensional space, millions of lines can be packed tightly while remaining nearly perpendicular to each other. Because of these geometries, weight matrices don't store just one clean fact per neuron, but dense, overlapping superpositions of knowledge. The multi-layer perceptron leverages this high-dimensional capacity through simple matrix math, providing the language model with a precise, elegant mechanism to perfectly store and retrieve a vast library of factual associations.